So section 5.2, we're going to start the last part of this course. Now, if I take you back a little bit, we started out this course with this example, where this was the number of COVID cases on average, or 7-week average, or 7-day average for a month and a half during 2022. So I replaced these with a model, so let's get rid of the data. And we started taking a look at where we're going to go in this course. And where we started out in this course was to try and find not the average rate of change, which is something that you'd be getting with just the slope of a line. We wanted to change that to the instantaneous rate of change. So we said, all right, well, to get the instantaneous rate of change, what we can do is take the limit, which is our first order of business in this course, and get closer and closer and closer to this point. And when they finally coalesce, then this is the instantaneous rate of change. What was it that measured the instantaneous rate of change for us? What in this course did we do that told us that? Derivative, yeah, thank you, the derivative. So once we finish that part, now we're going to start working with the next part, which is to try and find the area underneath this curve. So that exact area is not something you get with algebra or geometry because it's just a kind of a strange curve. So we're going to need to now use the opposite of differentiation, anti-differentiation, to help us figure out this area. So that's where we're headed. And what we're going to start out with is not the exact area, but an approximation to that area. So how are we going to approximate that area? Well, what we can do is take a curve, and if I want to try and approximate the area between, say, 0 and 2 above the x-axis and underneath this curve, there we go. There's my approximation. Is that a good approximation, do you think? Probably not. Now, we just did a handout from section 5.1. What could make this approximation better?
More rectangles.
Yeah, more rectangles. Thank you. So let's add another rectangle. And that's a better approximation. Notice the area went from 2 to 2.5. And, well, we probably get away with adding a couple more, maybe 3 or 4. And as we add more rectangles, the sum of this gets bigger. The sum of that is really adding up the area of all these rectangles. So let's keep going. And yeah, we get better and better approximations, right? By the way, what process is going on here right now as I increase n? Can anyone put that into words that relate to this course? What's the first major topic we covered in this course?
Limit.
Limits, yeah. You're taking the limit as n approaches infinity. And as we take that limit, these rectangles are better and better approximation of the true area. Now, with the left-hand intervals that we have here, we end up with an estimate of about 3.313. So, okay, not so bad, not so great either. The actual exact area is 10/3 or 3.333333. Let's change it up. What if I work with the right-hand rectangles? Well, then, same kind of thing is going to happen. This time I get a slightly overestimate. But one thing you might be curious about is like, well, what if we split the difference? What if we did, say, the midpoint there? Now what's going to happen? Well, now what happens is that this estimate gets really good really fast. Now, which one of these happens to work out best is going to change depending on the function and its shape. But here we get a really good estimate. So not too bad at all. Now, what's that going to relate to for us down here? Let's see how we're going to get that estimate. This estimate is called the Riemann sum, named after a German mathematician by the name of George Bernard Riemann. Some of his work helped out Einstein in his general theory of relativity. That's way beyond our course, though, fortunately. So let's remind ourselves of this notation. That's your sigma notation. So for instance, I could have the sum from I equals 1 to, say, 6 of, let's do I cubed. What that would mean is you start with I equal 1 and cube it. and then add I equal 2 and cube it, and I equal 3, and I equal 4, I equal 5, and finally I equal 6, and add all that up. So, okay, I'm not really concerned with exactly what that total is, but what I am interested in is you understanding this notation. This means a sum. Now, to try and estimate these areas, your Riemann sum is going to be a product of the areas of all these triangles, or these rectangles, I should say. So let's take a look at one of them in particular. Let's do this one, kind of highlighted here. Suppose you want to find the area of that rectangle. Well, how do you find the area of a rectangle in general? What's the formula for the area of a rectangle? Base times height, length times width, whatever you want to say. So the height of this, well, let's see, let's do the width. The width is given to us to be this delta x. Now you might remember delta x from our section on differentials. So delta x was related to dx. In fact, they were the same thing. But in this case, delta x is just going to be the width of this interval. Now the width of that interval is going to be the width of all these intervals divided by how many intervals we have. So that's our delta x is going to be b minus a over n. Now where are we going to measure the height of this interval? Well, that's going to vary depending on what approach you're taking. But for right now, let's just call it x sub I star. And let me x sub I star. That's where you're going to measure the height of your rectangle. So where you measure the height. So that's where you measure the height. But the question is, what is the height? So this curve here is some function y equals f of x. If I want to know the height of the rectangle at that particular point, then how would I find that height? What is that height? That's your y variable. So to get the y variable, I'm going to plug in f sub I star into the function. So the height is f of x sub I star. And if you look at this product in here, what you've got is the area of one rectangle is just this product. It's the height times the width. So height times the width. And together, that's the area of one rectangle. Now when you add up the area of all these rectangles, which is what that summation is doing for you, that's an approximation to the area underneath this curve. Now here's where our work with limits is coming back to help us out a little bit. This right now, as it stands, is just an approximation. But what's going to happen to our approximation as n goes towards infinity, as I let the number of rectangles increase?
It's going to get more accurate.
Yeah, it's going to get more and more accurate. And eventually, as you take the limit as n goes to infinity, it should actually equal the exact area. And that's going to be our definition. So our definition is going to be this. The limit as n goes to infinity of your Riemann sum is going to be denoted with this. The integral from a to b of f of x dx. Basically, what it is it's the area underneath this curve between a and b and above the x-axis. You're literally defining it that way. And the way we approach this has a lot of nice implications. I do want to mention one little quirk of history. Let me go back and remind you of something that we mentioned a while ago. Let's see, Newton, Actually, I think it was, I think I can find it here. Where is it? It was section, is there a section on Isaac Newton? No, that's epsilon deltas. Let me just take one more look. Newton's home. There we go. Oh no.
Oh, the triangle.
Oh.
The violin shape.
Yeah, it had, and I'm sorry my internet's down here, but it did have this shape on it. And the ironic thing on this is that this notation, even though Newton was the one that discovered calculus first, this is not Newton's notation. Does anyone remember whose notation it was? Leibniz. Yeah, well done. Yeah, this is Leibniz notation. So it's kind of funny that this symbol, which we're seeing here in this course for the first time, was actually on Newton's house. I have no idea what it represents. But for us, what you should understand is that this represents the area between the curve and the x-axis in the interval a to b. So it's just this area. So for instance, when we're asked in example A to try and find the integral from 0 to 14 of f of x dx, really what they're asking you to find is this area right here. Now we don't need any fancy calculus to find this area. What can we do to find that area? Any suggestions? Well, it's kind of the area of a trapezoid. And let me remind you of the formula for the area of a trapezoid. So, so we've got base 1, base 2, and a height. So if you want to find the area of a trapezoid, then there's a nice little formula there you can use. It's going to be 1/2 the average of these two times the height. So basically our area, and I didn't leave myself enough room here, area is going to equal h over 2 times b1 plus b2. So that's the area of a trapezoid, and we can use that formula to try and find the area underneath the curve between, say, 0 and 14 here for us. So let's do that. Let's see. That's going to be a 7. What's the height over here? 14, and well, these are in increments of 7, so that's going to be a 21, right? So I've got one side of length 21, another side of length 7. So that's going to be my B1 and B2. Call that B1, call that B2. And then this distance is going to be the height. So the area there, that's going to be, let's see, 14 over 2 times 7 plus 21. I think that's going to be 196. Thank you. So that's our 196. Nice. Let's try the next part of this. It says it wants the area between 0 and 35. Well, the area between 0 and 35, let's see, that's going to be right here. So we're going to have to add in another piece. So this area. So this answer is going to be 196 plus something. And now I got to figure out what that area is. In fact, why don't you take a second and see if you can't figure out what that area is. Again, you might want to treat it like a trapezoid. You could break it up into a rectangle and a triangle. There's nothing wrong with that. I mean, if you're not comfortable with the formula for the area of a trapezoid, hey, no worries. Just do a rectangle plus the area of that triangle. So that's going to be your 35 right there. So distance of 21. Actually, so I'm getting 294. Is that what you guys are getting?
Yeah.
Thank you. So the base here is 21, the height is 21, and the other base is 7. So 28 divided by 2 is 14 times 21. Is that right? Is that 294? Someone. Okay. All right. Thank you. So our total area then is going to be our 196 plus the 294. So 490 for the total area. So 490. Nice. So then we're going to go a little bit farther. And this time we want the area between, say, 35 and 49. So that 49 is going to be right here. So basically I want the area of this triangle. So at least we can get away from our trapezoid formula for a little bit. But there's something unusual about the triangle here. And that is when we find its area, because this is below the x-axis, its height is going to be negative. And we'll have what's called a signed area, which will be negative. So let's see if we can't figure out the area of this triangle. That's going to be 1/2 base times height. So the base in this case is 14. And the height happens to be a negative 21. So overall it should be negative 147. Negative 147. So that brings us to our last little piece here. And our last little piece is this part right here. To finish up, we want the area between 0 and 63. Let's go in a little bit closer. 0 and 63. So it's going to be this area. Again, probably the easiest thing to do, if you want to do that in one calculation, one formula, is work with it as a trapezoid. You could split it up into a square and a triangle. That works as well. Now, I don't know if you want to put the negative sign in associated with the area afterwards or during the calculation. It's kind of up to you. But let's see, it's going to be the height times the sum of the height divided by 2 times the sum of the bases. So let's see, the height is going to be negative 21. Let's see, no, the sum of the two bases. Let's do the height is this way. So the height is going to be 14 over 2 times the sum of the two bases, which is going to be negative 14 plus negative 21. And I don't think we're going to get something nice and even on this one. Are we? Let's see. No, yeah, we will. So it's going to be 7 times 35. So 245. But that sum is negative, so we'll end up with a negative 235. Now that's just the sum of the last piece. What's this thing overall going to be if I ask you to find the area between 0 and 63? Yeah, you're going to have to add up all these areas. So it's going to be 196 plus 294 plus negative 147 plus negative 235. So let's start out with the 490.
Is it 235 or 240?
I got 245 as well.
245? All right, thank you. 245. Thank you. All right, so basically 490 minus 147 minus 245, and we end up with 98. All right, so not really engrossing or entertaining calculations here, but the big point is we're starting to marry this new notation with the idea of an area. So this new notation is our definite integral, and it's going to be interpreted as the area between the curve and the x-axis in some interval. Now, in the case of a function that happens to be below the x-axis, you'll end up with a signed area. That signed area is going to have a negative sign to it. So, okay. Overall, which area do you think is bigger, the area above the x-axis or the area below the x-axis? Good. Why above? Why is she right by saying above? Looks bigger. Is there an objective way to say that it is bigger? Numbers are larger. Okay. And overall, we got a positive number here, right? So the positive here minus the negative here end up being positive, so this has to be bigger. So just a little exercise and some thinking there. Let's keep going. Now some of these you're going to actually have to draw to try and find an interpretation. So let's do that. Let's start out with example D, which is the integral from 0 to 9 of 1/3 x minus 2 dx. Okay, well, let's think about what that function is going to look like. So in particular, I want to graph y equals 1/3 x minus 2. What's that graph going to look like? All right, a line, good. And let's see if we can't draw that line. What can you tell me about this line?
Starts -2.
All right, starts at -2, so the y-intercept is here at -2. Where is it going to end up? When x equals 9, where is that going to end up? How would you figure that out? Where is it going to end up?
Plug it in.
Yeah, 1/3 of 9 is 3, minus 2 is 1. So up here someplace. And I think it's going to be important to know what the x-intercept is. Where is this going to cross the x-axis? Now, note, this hasn't been drawn wonderfully to scale. That's okay. How am I going to find out where this happens? Yeah, set y equal to 0. If you set y equal to 0, you end up with x equals 6. So, all right. So we need to find two areas. That's going to be this one here. And then this one here. Now you can't really decide based on the graph here because this isn't drawn to scale. But I think we're going to end up with a negative number. So we need to find what we'll call A1 and A2. These are both triangles. So A1, remember the formula for the area of a triangle? Yeah, 1/2 base times height. So let's call this the base, which is going to be 6, and the height I'll call -2. So I end up with -6. How about A2? 1/2 times what times what?
1/2 times 3 times 1.
Yeah, 1/2 times 3 times 1, basically 3/2. If I want the total area now, this is just going to be, let's see, let me bring you down here. A1 plus A2, -6 plus 3/2 will end up being 9/2, -9/2.
Do we need to leave it a fraction?
If you gave me a decimal, I wouldn't complain. Although I prefer fractions, especially mixed or improper fractions. But if you gave me -4.5 or -4.5, I mean, it's still the same answer. I'm not going to really worry about it. Nice, nice. Let's jump up to example, the third one here, example F. So we'll skip example D, or example E here. Let's do example F. This time we've got the integral of an absolute value function. I'm not sure that many of you would visualize too easily what the graph of the absolute value of 2x minus 3 equals looks like. So if you can't figure out, well, what it looks like, then what would be your recourse? How are you going to find what that graph looks like? Yeah, graph it. Graph it. Put it in your calculator. Right. Now, as far as where to graph it, you've got kind of a hint here. The limits on our graph are going to be between 0 and 3. So as far as setting up our window is concerned, we'll use that. And there we go. Let's go to the y equals key, clear out some stuff from last time. At least last time for me. Where do I find the absolute value on our graphing calculator? Yeah, the math menu, and then go over to number. The first option there is your absolute value. We want the absolute value of 2x minus 3. And let's set up our window between 0 and 3 on the x-axis. And it's probably been a while since I've shown you, or maybe I didn't show this class at all. But there's a way to make your calculator handle the rest of this, right? Because we need to figure out, well, where are you going to graph it on the y-axis? The way to make your calculator figure out the y variables, the y scale, and min and max, is to hit zoom and then 0. If you take a look, zoom 0 says zoom fit. What that'll do for you is it'll let your calculator say, all right, I'll figure out what y values you need, and we'll just plot that. So there you go. There's your graph. Looks pretty nice. Just kind of a V. Any guesses as to where this graph touches the x-axis? Yeah, 1.5. Exactly. And you can actually solve for that by setting 2x minus 3 equal to 0. And you'll get x equals 3/2. Yeah, yeah. If you just hit the trace key, and it puts something right in the middle of your graph, which is at 1.5 and 0. So yeah, well done. All right. So let's see. Now it's nice that we did the trace key, because now we don't actually have to think. One of the things I'm going to need to know is what's the height at 0. Oh, and the height at 0 is 3. Okay, so nice. So my graph looks like this. I want to find the area of between the curve and the x-axis here. how would you do this? What would be your MO on this one? So 0, 3, 1.5 and 0, and 3 and 3. What would you do to try and find the total area between the curve and the x-axis? Any suggestions? Area of triangle? Do I need to add up the area of both triangles? Keegan, what would you do?
3 times 3 divided by 2.
I'm not sure. 3 times 3 divided by 2. That would be like the area of half of the square. So let's keep in mind what we're asked for in this one, and that is this area right here, this much here, and this much here. That's what this is asking us for. Is there a shortcut that I can take in my calculation here? Well, let's just try and find the area of the first rectangle, A1, A2, or not the rectangle, the triangle. So A1 is going to be 1/2 base, which is 1.5 or 3/2, times the height. What's the height here? 3. So we'll end up with 9/4. Now I got to repeat that over here, right? Or do I? Yeah, it's the same thing. That's what I was trying to get at, is that it's the same thing. So the total area here, this integral from 0 to 3 of the absolute value of 2x minus 3 dx is really going to be 2 times 9/4, which is going to be 9/2. If you wanted to write 4.5, again, I'm not going to complain. Now there's some properties of integrals that are really nice. That doesn't always work in mathematics. A lot of times things that you would like to be true aren't true. I'll give you a few famous ones, at least famous in my mind and those of other math instructors. It'd be nice if the square root of x squared plus 4 was x plus 2. X plus 2. But it's not. It'd be nice if the log of x plus 9 was equal to the log of x plus the log of 9. But that, again, that's not true. So it's refreshing to see something in mathematics that actually does work kind of like you would hope and what you would think. And we'll see some of that here with this example. So let's work with example G here, and we'll discover some of what's called the linearity properties of the integral. So example G, the integral of, or from 0 to 1 of 7 minus 3x squared dx. And as a side note, they did mention for us that the integral from, integral from 0 to 1 of x squared dx is 1/3. Okay. Well, there's some properties of integrals that we're going to use here. And let me kind of briefly sketch out what those properties are. So, properties. Properties of integrals. The integral from a to b of a constant times f of x dx. That constant can come out in front. So it's going to be c times the integral from a to b of f of x dx. So that's kind of nice. Another property, again, these are some of the linearity properties of integrals, would be this one. The integral from a to b of f of x plus or minus g of x dx. You can split that up. You can rewrite that as the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So those are some nice properties that we're going to take advantage of. And they reflect kind of the additive nature or the addition that you do with your Riemann sums to get some of these things. So some properties of integrals that we're going to keep track of. How does that affect us here? Well, I'll start out by separating this. That'll be the integral from 0 to 1 of 7 dx minus the integral from 0 to 1 of 3x squared dx. Okay. And there's something else I can do with this second one. Does anyone see what that is? Yeah, that 3 is going to come out. So I'll move that to 3 times the integral from 0 to 1 of x squared dx. And this works out kind of nice here. Does anyone know why? You're told in the problem that that's actually 1/3. So we're going to end up with 3 times 1/3. So minus 3 times 1/3. But now I got to envision the rest of this. This is going to be the integral between 0 and 1 of the function 7. What is y equals 7 going to look like in terms of a graph? Any thoughts? Any suggestions? What's that going to look like? Say again? Horizontal line. Yeah, it's just going to be a horizontal line. So if we were to graph it, let's see. Let me do it here. That's just a 7 between 0 and 1. Okay. What does this evaluate to?
7.
7. Yeah, it's just the area of this rectangle, right? So that's going to be a 7. So we'll end up with 7 minus 1, which is 6. Nice. Really nice. So a lot of this stuff is just kind of definitions and introducing you to some of this notation. But this is a nice one. It's just the linearity properties of the definite integral. And we're going to see and do much more of this. But for right now, I think we nailed that one. Looking good. Let's move on to example G. This one's kind of going backwards. It's working back towards what we started out with in terms of the definition of the Riemann integral. So definition starts out with a limit and gives you the integral. Let's see if we can't change this into this. Now they tell you the limits over which they're working. So this is going to be the limit from 0 to 1. 0 to 1. And this part here is going to be my function. This little piece here, remember I mentioned this earlier. I reminded you that delta x and dx are the same. So I'm going to have a dx here. But in between, what I've got to put is the function. What function is this? Well, right now they substituted an x sub I, wherever we have an x. We don't have to do x sub I, we just got to do an x for a variable. So let's take a look at that function. In the numerator, I've got e to the x. In the denominator, I got 1 plus x. And that's it. You're done with this one. It's just asking you, do you understand this notation? So why don't you try the next one or the next two? See what you can come up with. If you're watching this later, try and pause this and come up with the same things we do. Let's take a look at this first one. So the integral is going to be between 2 and 5. You get that from these limits here. What's the function in here? What does this represent? X times the square root of 1 plus x cubed. Yeah, I had to look at that kind of closely. Dx. And that's it. Let's move down to the next one. So for the next one, this is the integral between 2 and 7 of 5 times x cubed minus 4x. Please don't forget about that dx. It actually does have some significance, importance, and relevance, and I do want to see it. But as far as this problem is concerned, that's it. I'm hoping that if it put problems on an exam like this, you'd like, yeah, his favorite team must have won over the weekend or something like that, because these should be pretty easy. I'm hoping.
You don't separate out the 5x cubed.
Oh, as far as evaluating it is concerned, yeah, you could do that.
Okay.
But right now, for the first step, just to write this down, this is good enough. Yeah, eventually, in terms of evaluating this, you could rewrite it as 5 times the integral from 2 to 7 of x cubed dx minus 4 times the integral from 2 to 7 of x dx. So yeah, going beyond this to try and start evaluating these things, yes, you are going to do a little bit more work. But the problem here is only calling for us to try and rewrite this using our integral notation.
Okay.
So the last one, integral from 1 to 3 of x over x squared plus 4. And don't forget that dx, please. Okay. Let's keep going. Example I. Let me try and give you a visual understanding of one of the rules that we're going to use in example I. Let's do this. Let's suppose you have an integral from a to b, so this is y equals f of x. And if I wanted to find the area underneath this curve, it would be the integral from a to b of f of x dx. That's the area underneath this curve. But let's say that I have a point somewhere in between here. Call it C. Then another thing I can do in terms of finding the area, if and where I find it convenient, is I could break this up into the integral from a to c of f of x dx, which is just the left half, plus what else? What would I need to finish it off with? C to b of f of x dx. So you're splitting it up a little bit. Okay, looking good there. Trying to think if there's one more formula I'm going to need to give you or not. Let me look at this last one here. All right, so let's put these two together, kind of using this idea right here. What I want you to notice about this one is that these two limits are the same, right? So you can kind of squeeze those together. How would I rewrite this? Oops. Minus 4 to 3 of f of x dx. And then I'm going to subtract off a little piece. I'm going to subtract off the integral from negative 4 to negative 3 of f of x dx. And maybe it would help to draw this a little bit. So let's see if we can't draw that and try and understand a little bit about what's happening here. So this is example I. And I want to graph this function between negative 4 and 3. And negative 4. So what I've got here in this first part, let's see, we've got the integral from negative 4 to 3 of f of x dx. That's this entire area, right? But then I'm going to subtract off a piece. And that piece I'm going to subtract off is the integral from negative 4 to negative 3 of f of x dx. And let me zoom out a little bit. Oops, wrong way. Nice. So what's happening here? I've got this whole area and I'm going to subtract off that little piece. So what am I left with? What should I write as the result of this subtraction? What's that going to equal?
Negative 3 to 3.
Yeah, negative 3 to 3. So what you're left with is just this piece right here. And thank you so much, Christian. From negative 3 to 3 of f of x dx. Okay, that's all they're looking for on that one. Okay, we're going to have to do a part 2 on this next week. For now, we'll stop it here. But there's certainly some heavy lifting ahead of us. But for right now, this is part 1.